I think SEM is one of the most underrated set of techniques, and I'm very delighted that we're doing this workshop that combines SEM as a platform with a lot of analytical techniques. And also what's so special about this event is Hitachi and Oxford collaboration that we have with Nuance, and they brought in the best technical people, and that's a unique experience for all of you. So this is one of many such events we organize at Nuance, as most of you know. And this is the topic, it's timely. These are the capabilities either we have at Nuance or we intend to. And I think this can serve as a guide for many of you who like to learn about new techniques, new methods. Please do let us know if there's a special topic that you'd like us to organize events such as this. In the meanwhile, I just want to acknowledge and applaud Tears, Katie, and all the organizing committee for pulling this event together, and particularly to Hitachi and Oxford for collaborating with us and sending the people to interact and engage with the community. So I don't want to take too much time except to say that welcome again, and I enjoyed the workshop. I'm particularly intrigued by the STEM aspect of imaging within SEM. And that's really a growing area of great interest to both soft materials as well as soft and hybrid. So I look forward to learning from the experts, and please do engage actively, ask questions, and look forward to a very productive day ahead. Thank you. Teresa, back to you.
Thank you very much for the very warm welcome. And it is our pleasure to introduce Atsushi Muto from Hitachi High Technology for the first talk this morning. So Muto-san, if you'd like to take it away, thank you so much for joining us.
Thank you very much.
Before it begins, let me just quickly say a very nostalgia with Muto-san being here. I remember we hosted you for many years ago, and we're delighted to have you back, Atsushi, and enjoy the event and look forward to learning from you.
Thank you very much. Yes, so give me a chance, time to open up. Yeah, okay. So thank you, Vinayak and Nuance members, to giving us such a great opportunity. And yes, hello, Nuance users and everyone. Yes, my name is Atsushi Muto. Yes, a Hitachi application engineer. Today, I would like to talk about the SU8030 UHRF SEM capability. So, yeah, Vinayak shortly, yes, and kindly introduce me. But yes, just quickly, yes, I'd like to introduce myself. Yes, I'm currently assistant manager in the application in Hitachi High-Tech America and working in Clarksburg, Maryland. So, yes, my job is application engineer, application development, collaborating researches, and especially including the field emission SEM. So also I had an opportunity to stay at the Nuance Center from 2007 to 2008 as an invited scientist. So yes, my feeling is I'm a part of the family of the Nuance member. Thank you very much. So let me start from the, yes, today's presentation. So give me a moment, I will change to the presentation mode. Okay. So first, let me introduce, yes, review the Hitachi SU8030 field emission, yes, specifications. So specification information bullet point is copied from the Nuance, yes, website homepage. And yes, SU8030 is a successive model of the S4748. It's also very popular field emission microscope as a high resolution with more imaging capability models. Yes, yeah, that tool is released in 2011, and yes, Nuance, yes, purchased and installed the tool in 2011 at the same timing. Thank you very much, and using a very long time with very nice conditions and performances. So this is today's agenda. Yes, I would like to review. We'd like to review SU8030 capability, and yes, if you expect beyond current SU8030 capability. So just in case, I'd like to introduce some of the topics currently completed or achieved by SEM. So my goal of the presentation, this is my point of view, help Nuance 8030 users to find new application solution using SU8030. So yes, for example, this is just my thought that I'm using the, I used to give up observing the small nanoparticles, but after seeing the presentation, it seems possible from tool performance point. So if you feel, yes, let's work with Hitachi application engineer, me and Nuance members to find the better way. And also share a few examples of Hitachi's latest application using SEM to help users having requests beyond the SU8030 capability. Yes, if you are interested in beyond the part, yes, please feel free to contact to Hitachi members. Thank you very much. So first, let's start from the fundamental point, how small structure our SU8030 can resolve. So this is an example of the observing catalyst at the landing voltage 15 kV. So if you use a high voltage, we can achieve the very high resolution. And yes, as I show in here, arrows, we can resolve the 1 nanometer or smaller size particle structure by SU8030. And of course, you are operating SEM very frequently, and you think, yes, high voltage we can get the resolution, but what about the low voltage? So this is an example to observe the titanium dioxide nanoparticles used for sunlight reflection. So we are observing at the 3 kV. And yes, we can see the very fine surface features. So surface area is an important point for the performance. And we can see the very fine 2-3 nanometers, surface topography, fine profile. So this is a kind of the performance 8030 can achieve at the low voltage. And this is a good seminar opportunity to learn the SEM optics in detail. So I'm sure most of you know, but it will be good to review why SU8030 can perform such a high resolution. So one of the most important part is the emitter part. So SU8030 uses a Hitachi in-house manufactured cold field emission emitter. So characteristics of the cold field emission is showing at below. Cold field emission emitter has the advantage of the small energy spread, very small source size, smaller than 5 nanometer, and high brightness. Even in a small probe, we can get a good signal contrast. So we don't have to emit so much probe. So that contributes to keep the probe size small. So, and this is a advanced opportunity to show a little more why we can get high resolution. So to get the high resolution, actually pure secondary electron detection. This is a very important point for the successful imaging. So I'm just showing the internal objective lens structure diagram of the SU8030. We are detecting the pure secondary electron to be screwed up and using the microscopy filter that venting the signal to the detector. And currently, you will see the blue line that are backscattered electron. Actually, if we backscattered electron have a little unique taking trajectory to normally hit in the inside of the lens structure. Once backscatter hit in the inside lens structure, it will generate the secondary electron. That secondary electron don't have a resolution information. That secondary electron has backscatter oriented information. So if we detect this secondary electron signal, that makes a noise or contamination of the pure high resolution secondary electron image. So currently, it's a small tips, but we are applying the positive voltage. It's at the electrode side of the inside column to trap the secondary electron so that we can only detect the pure secondary electron. So this is one of the technology, but to combine of this kind of the technology to detect the pure secondary electron contributes such a high resolution of the SU8030. And of course, yes, I'm showing the ideal imaging case of the samples, but in fact, your sample has, of course, lots of different types of samples and different artifact or tough point to overcome. So we all know, through site has a performance, but the most important part is our operation. How to set the accelerating voltage, just showing in a diatom example, showing the left side. So by changing the voltage to the higher to lower, we start to see more surface information, but we know, we lose the resolution. And condenser lens settings, aperture settings, that control the sharpness and signal. Yes, we have to find out the appropriate compromising point by our operation. So if you feel we'd like to try better image, and if you need any support, from the Hitachi or Nuance members. So today and tomorrow I'm at the Nuance Center, and if you can bring the sample, reserve the time. So we are happy to work together. So let's find the best imaging condition of your samples during demo session. So next is also unique capability of the SU8030 diverse imaging capability. SU8030 has three different detectors. And I'd like to show some of the examples highlighting the unique imaging capability of SU8030. So this is an example to observe the Arctic ceramics. So you can see base material is alumina, and the titanium carbide material is distributing around. So we are seeing the composition contrast clearly, but I'd like to emphasize is this accelerating voltage. So SU8030 has a very unique high backscattered electron signal detection yield even at low voltage. So why low voltage backscatter is important? For example, if we observe these ceramic samples, so at the different backscattered, different voltage at the backscattered electron signal. So I'm just showing that a cross-sectional diagram to help your understanding. So backscattered electron signal source becomes deeper and deeper by increasing the accelerating voltage. So if we use the high voltage, good point is that we can pick up the signal, but if you'd like to see surface detail, internal information becomes contamination and difficult to understand the real surface composition profile. So I think you all know, but it will be good to review. Why backscatter low voltage is important to confirm the secondary electron signal and the backscatter the electron signal, signal source depth information. So currently we are showing the secondary electron signal. Secondary electron signal is generated from the close to the surface, but the backscattered electron signal is generated from the whole scattering area. So this whole scattering area is completely changing by the accelerating voltage. Changing the accelerating voltage higher, so makes the scattering volume deeper, and backscattered electron signal is relatively losing the surface information. So how yes, SU8030 can detect the backscattered low voltage backscattered electron signal. So yes, I'd like to show using the these diagrams and videos. So we are seeing the same objective lens cross-section diagram in the secondary electron detection. So secondary electron, now we are showing the secondary electron detection, and currently showing the backscattered electron detection. Now, what's the difference from the secondary electron detection is we are changing the electrode, internal inside objective lens electrode bias to the negative direction, opposite to the positive for the secondary electron. What happened to the signal behavior of the secondary electron and the backscatter is so backscattered electron signal hit to the inside of the objective lens, but this lens electrode is negative. So secondary electron is now released from the electrode and going towards the secondary electron detector. So normal pure secondary electron is blocked by the very strong negative electron field around the bottom of the objective lens. So by this way, we are kind of filtering the secondary electron signal and allowing the secondary electron having a backscattered electron signal. So by this conversion way, we can detect the backscatter signal. And this signal detection method is very beneficial for the low voltage backscattered electron detection, because finally we are detecting the signal in secondary electron. So this is a little, messy slides. I quickly made that, but so yes, my question is, did you have a chance to use the LABSE? So to corresponding to the cross-section diagram, if you select LABSE, internal electrode of the objective lens changed to the negative. And how much signal filtering, energy filtering we are making. So you can see SE suppress. So this number, it's an arbitrary number, but yes, it's a seminar timing, so will be good to show. So 0 is 0 volt, and 100 shows a negative 150 volt. So if we give higher number, we are giving the stronger negative voltage to strongly suppress the secondary electron, pure secondary electron signal, more close towards a pure backscatter signal. So in case if you see the LA55 in your data bar, so it means how much voltage we are applying. So this is a simple calculation, and we can understand this is a negative 82.5 volt applied. So yes. Also, this is one of the reference. Also, low voltage is very important for the EDS mapping result. So this is an example to observe to EDS mapping of the same aluminum titanium carbide material at the 2 kV and 10 kV. So 2 kV and 10 kV is as shown in the Monte Carlo simulation diagram. So scattering volume is quite different. And 2 kV, we can detect the very surface-oriented composition and X-ray data. So interface, we can see the very clear interface and the surface-oriented EDS mapping. If you use a high kV at the same area of interest, yes, beam is penetrating to very, very deep. So that will, making some mixture of the internal information. Yes, so, and it is very difficult to see the real surface EDS mapping data. So if you are observing and doing the EDS analysis and motivated to try the low voltage, yes, I'm sure we have a chance to try together for the EBS data with Oxford people and to improve the quality. So this is another application, to use the low voltage backscattered electron detection. So this is a biological section, rat cerebellum. and we are observing both low voltage 1.5 kV and 3 kV. So at low magnification, it seems the same of the information. So this is a stained material, but if we zoom in, as you can see, 1.5 kV low voltage can resolve the surface features very well. So we can see the better interface information at 1.5 kV backscatter rather than 3 kV. So especially for the biological sample, even if we stained, so most of the structure is consisted by the carbon and oxide, very low atomic number materials. In this case, beam penetrates deep, and even at low 3 kV, 5 kV, we are picking up the deeper part information. So low voltage backscatter is a key for the successful image. Also, have you ever tried to observe the crystalline contrast, getting the crystalline contrast using the 8030? Actually, I'm not so much chance to see users enjoying the this type of imaging in SU8030, but the SU8030 has a dedicated detector for highlighting this kind of crystalline information. So this is a recording disk media, and we are using the 1.2 kV. Normally, when we use a low voltage, we can clearly observe this kind of crystalline information. This is amorphous or crystalline information. So how we get that? So we are using the high angle backscatter top detector. So it is very simple detection principle. So secondary electron is going to the upper detector, and high angle backscattered electron is detected by the top detector by this showing this type of movie. So by this way, we can detect the very high contrast, high sensitive crystalline information. And if you'd like to emphasize the topographic information, it is very popular, I think, for you to use a lower detector. So lower detector is equipped to our SEM chamber, so giving the shadowing effect for the signals orientation, so we can get the very topographic information. And this is a different level of the topography visualization. So how small topography our SU8030 can visualize. So this is an example to demonstrate 1.5 nanometer step structure, terrace structure of the pentasyn organic thin film transistor. So using the very low voltage, this is a 100-volt landing voltage. We can limit the source size very shallow and can resolve such a small step structure. How we make that? This is one of the, also we confirmed this step size by, AFM. How we make that step structure? So we are using deceleration technology. So we'll review and confirm the operation in live in my second session. So this, let me show the rough diagram, rough signal behavior. So applies negative voltage to the stage. So secondary electron is completely straight up and detected by the top detector. And the backscattered electron and topographic information is have a small, little wider angle and detected by the upper detector. So role of the top detector and upper detector is completely opposite when we use the deceleration. It's a little complicated point, but we'll review in live session, second live session. So by using deceleration, we can yes, we can realize the 100 volt low voltage, ultra low landing voltage imaging. And the low landing voltage is also one of the other benefits of the low landing voltage is damage, less damage. So this is a kaolin, pigment material, very sensitive to the beam damage. We have two images. I took the image at 100 volt and getting the image next by the 500 volt. So you can see 500 volt, we start to see the kind of topography, like a start to bubbling. So that's a kind of deformation of the surface features. So by using the low landing voltage is very gentle to the surface. And yes, if you are struggling by the beam damage or deformation of the samples, it's worth trying the deceleration technology and 100 volt, 200 volt. So here's a review of the SU8030 capability. So imaging of fine structure below 1 nanometer, low voltage backscatter imaging at 1 kV and below is possible, available. Crystalline contrast enhancement, topographic contrast enhancement, and fine topography visualization about 1.5 nanometer, beam sensitive material imaging at 100 volt. Again, yes, your sample is of course maybe have more difficult point or tough point. So yes, to achieve the successful imaging, healthy tool status that is on Hitachi and Nuance Center members, and appropriate imaging parameter setting that is done by you by support of the Nuance and our vendor. So if you have any tough sample but motivated to try better imaging, yes, let's find the imaging, best imaging condition of your samples during the demonstration together. So this is a SU8030 imaging capability review part. So currently, I have 10, 15 more minutes. So yes, let me go to the next session of if you expect beyond current SU8030 capability. So this is kind of the transition of the image quality by time and tool. So yes, I'm sure I should say I see 8030, our 8030 resolution is still really good. But of course, 10 years time is, of course, vendor is working hard to improve the resolution. So this is the current imaging performance of the current tool. Successive model is a SU8600. So if you try your best using 8030 and your skills, operations, optimization, but you think we need a little better resolution, yes, please contact Hitachi and we are happy to support you. And also, other point is, landing voltage lower than 100 volt to reveal top surface feature. So this is an example to observe the metal surface features. Yes, by using the AFM and other analytical technology, we know, we have a very thin film structures or very fine features on the surface, but sometimes very difficult to see by SEM. So now I changed the 5 kV secondary electron from backscatter, changing the 1 kV. Yes, we start to see some thin film layers, but once we change to the 50 volt, we can see the quite different world. That's what we understood. Yes. So we can see the very fine particle structures and more layer structures. So that imaging is done by the passive voltage contrast imaging at really low voltage from 10 volt to 50 volt. So if you have tried to imaging, for example, 100 volt to 200 volt by using 8030, but still you think I'd like to see a little shallow or more surface-oriented information, yes, that's the time I think we can help, and we are happy to explore yes, 50 volt, 30 volt, 10 volt imaging to help your research. And the other part is automation. Yes, I hope you enjoy operating the SU8030, but I'm sure you have to do lots of things. For example, writing a paper or summarizing the data, and sometimes would like to have a rest, of course. So in this case, I think you think, yes, if the SEM can automate, yes, automatically work kind of the complex, yes, our workflow, imaging workflow, moving the stage and doing everything. So currently we have recent tool have a EM flow creator that is yes, a recipe function. So yes, no programming skill is required. You can see the yes, a screen, yes, a user interface at the right side. So command menu area, command parameter setting, and automation flow. Very intuitive automation. And good point is, of course, if you are, yes, research is complex, working with EDS or working with particle analysis, yes, this EM flow creator can accommodate, yes, includes a Python-based script. So if you are familiar with Python, you know, yes, we can do almost everything. Can make the customized CSV file or customize the user interface and working with SEM. So these kind of things we can realize now. So just this is a movie file showing the examples. What I'd like to do, yes, I'd like to set up the recipe. Just selecting the major part, we can select magnification, and how much magnification we'll just going to the input area and giving the idea, information input. Yes, so like this way, yes, very easy, and introducing the ABCC and others. So from the, just drag and drop and giving the parameter and can make the whole worksheet. So one of the example is also, recent automation technologies. It has, including some template matching and judging process. So yes, let me show the one of the a little more extensive workflow example. So now you can see the lots of particles in a SEM image. So I'm trying to let the system to recognize the target particle, circular particle, then centering at 700 magnification, fine centering 3000 magnification, and changing the magnification up and beam adjust and capture. So if I'd like to do all, I make a recipe. Then just demonstrating how it works. So what I will start is of course play, execute the recipe, and each process will be highlighted when during the process. So first, getting the image, then pattern recognition is working. Yes, here's a circular particle. Now travel stage automatically. Yes, I have a better. Yes, it's better. I have a better stage. Yes, still not completely center, but by changing the magnification and recognition and travel stage automatically to center. Yes, now it gets, after getting the center, changing the magnification higher, ABCC, AFC, and capture image. So, and we can successfully do this kind of whole process. So, if you have any kind of the interest about the automate, can this EM flow creator can work with our expectation? Yes, so please contact Hitachi, and we are happy to try. And also, another example is if you expect that it's a tool site, a preparation tool site. So have you ever seen the kind of the situation in slides? So we tried to cleave the sample, but to see the multi-layer structure. But yes, cleaving surface is not smooth, so it is very difficult to see the structure in detail or thickness information. Or if we polished carefully or epoxy embedded metal sample, but didn't see the grain, yes, my polishing is not good or sample is really difficult. So in this case, I think our ion milling system helps you to get the best data. So this is a, yes, the right side image is data taken by the ion milling system. And the fact is, I'm sure, yes, this is your tech, prep room. And we successfully installed and launched the Hitachi's ion milling system. Yes, I cannot, I'm not a decision maker, but I'm expecting to leave that until end of October or longer. So yes, so this is milling system, prep system. Principle is a broad ion etching system. So using the argon ion to clean up or making cross section of the sample. So how difficult to use? Just one of the, I'm going to show the one of the example, how to set the sample in a movie. So epoxy embedded sample, it's on a sample stab and put the plastic cap clip to flash the sample top surface to the every time same constant of the area, top of the ring. Yes. So after setting the sample, it's easy just to put the sample to the holder, then vacuum and set the beam. That's it. So yes, I have to fix the sample by the hex wrench. So it's quite easy to prepare and easy to operate. And also, stage chilled.
That is mine.
Is that moth mine?
That's not mine.
Can you make me one too?
Okay. Yes. So yes, and this one, yes, in case of this one of the function flat milling, we can change the stage against the argon beam tilt angle. So by changing the tilt angle, this is a mechanical polished materials, solder based, plating based materials. And if you set the angle more perpendicular to the argon beam, they are emphasizing the etching effect of the material. So by the topography, we can differentiate the material information. And if you just would like to clean up the surface, yes, we'll just keep the sample parallel, close to the parallel to the beam. So beam is gently clean up the surface. So that will be, I think, ideal case for the EBSD analysis. Okay. Yes. So yes, if you, last time I said, tool condition and your judgment is important for the best imaging, but I have to correct my statement. Appropriate sample preparation, upper side, yes. This is the most important part for the successful imaging and data acquisition. And I'm hoping, yes, my experience and also this broad ion beam can help and improve your data from the sample preparation point of view. So this is a summary of my presentation. So we debuted SU8030 unique capability. And yes, in case if you expect beyond, yes, we introduced the high resolution, lower landing voltage, automation, and the sample preparation. So I hope I have a little couple of minutes. So I just would like to also, I introduce my second session. Sorry, first session, I'm doing all from my laptop, but the second session, I will show live imaging. I operate the SU8030. So first one is STEM by SEM. So if you are expecting to simultaneous imaging of the secondary electron and STEM imaging, like a carbon nanotube in upper side and the core shell structure of the nanoparticles of the left lower side, yes, it's worth trying to use a STEM function in ISU 8030. Yes, how difficult is operation? How to set a sample? Yes, I will explain a little at the beginning of the next session. And the deceleration technology. Yes, I'm showing the a kind of the image quality transition slides in the in previous presentation. And from 4700 to the 8030 generations. So what makes this low voltage resolution imaging capability improve? It's one of the biggest improvement factor technology is this deceleration technology. So if you have a reason to observe the sample at the relatively low voltage, for example, to observe the surface feature or to control the charge up, or to reduce the damage. So, but had a trouble to get the high resolution. So let's review deceleration technology. So deceleration technology can again improve resolution at low voltage, reduce the beam damage, and visualize 1 to 5 nanometer very fine surface topography. So yes, I'm looking forward to reviewing these two items at my second live operation session. Thank you very much for your time. So if you have any questions, yes, I'm happy to receive.
Thank you so much, Muto-san, for your amazing talk. We will
Thank you.
probably save some questions for the break so we can move along with our next speaker. And so it's my pleasure to introduce Mike Helmstead, an applications specialist from Oxford Instruments Nanoanalysis. Many of you that are our users here at Nuance, whenever we say we're going to ask Oxford Instruments for technical advice on your problems, you're usually talking to Mike. So thank you, Mike. So without further ado, Mike, why don't you take it away?
All right, can you hear me all right?
Yes, we can hear you.
Okay, you can see my screen, I hope.
Yep, we can see your screen. Yep, there you go.
Perfect.
Thank you.
Thank you for the introduction, Tears. I appreciate it. Always happy to help out at Nuance. I'm kind of glad I'm almost considered the Oxford person when you bring someone technical involved. So it's good to be here this morning and to talk to everybody. And what I wanted to talk about was an introduction to energy dispersive spectroscopy, so EDS. So it's really the it's really the big ticket item for Oxford Nanoanalysis. I mean, we do several other things, but this is really the bread and butter. So, I wanted to kind of give a brief overview of what the science really is, get you kind of introduced to it, and we'll, I have an agenda, but what are we actually talking about with EDS? Where are you measuring it from? And kind of want to get into how the detector actually works. I'll talk about Ultimax a little bit more, but when I talk about the detector, it's going to be kind of a generic SDD discussion. We'll talk about what that acronym means as we go along. And then I do want to kind of talk about the Aztec software. Change the agenda a little bit. We won't demonstrate that basic qualitative and quantitative EDS necessarily, but it's something that we'll probably have time during demo sessions and other things as we go. The nice part about this presentation is it leads into what we'll talk about a little bit later too, and want to go into more depth on a technique called Lair Probe, which is something for kind of layered materials, 2D materials, working with thickness and composition. So this is leading really well. So when we talk about EDS, what really are we interested here? Let me close this window here really quick. Sorry. We want to talk about the electron beam in the SEM and what it's actually doing, what it's actually creating. And there's a number of different events that you can talk about. You can talk about elastic scattering events like just backscattering, and Muto-san gave a nice talk about how that's beneficial for imaging. We can talk about EBSD all day if you want. I'm happy to do that, but it's a little bit irrelevant today. So we'll leave the diffraction signal off to the side here. What I'm worried about for EDS is the inelastic scattering events. And there's a couple that are listed in the slide here. We talk about single electron scattering, boson scattering, plasmon, cathode luminescence, O-shape. But what we're interested in is the X-ray emission. And come on, slide, there we go. I'm interested in the characteristic emission, and kind of as a side to this is the continuous X-ray emission, the continuum X-ray, if you will. So really, when you look at an EDS spectrum, which has just come up in front of us here, the characteristics are something specific to the material. Continuum, just kind of background X-rays. And kind of a better way to see it is to really actually look, I got ahead of myself there, pardon, is to break down, really what's going on in the atom from right down to the Bohr model here. And when we talk about characteristic X-rays, and I know this animation's a little bit on the, it can be a little bit on the fast side there. I guess it didn't trigger. Sorry about that. So yeah, so what we're talking about is the incident electron coming into an orbital shell here and actually knocking out an electron that's actually in the specimen shell. And it'll open up a spot in the atomic structure, and basically what we're doing is we're backfilling that, and depending on where you start from or where you're going, you kind of create different characteristic X-rays. And there's kind of a transition that's drawn on the right hand side there with the K alpha versus an L alpha versus an L beta. And really, for a beginner in EDS, I always tell them, just worry about where the electron is going, what jump it's making, because that's how we determine the lettering of the X-rays. So when we talk about K X-rays versus L X-rays, it's all about kind of destination of the electron. So these are specific transitions in the material. So this is why when we look at a spectrum at the end of the day and I see something like 8.04 kV, I know that's my copper K alpha line. I know it's specific to copper. It couldn't be something else. Certainly there's overlaps that exist, but each one kind of has their own characteristic energy. So the other side of this is continuum X-rays, and these are really background X-rays, and they're, I wish I could get my hand. Oh, there's my animation. But imagine the electron coming in and basically not making a complete knockout, if you will, of an electron in the orbital, and maybe making a change of direction. In that case, you have to kind of maintain your energy, and you're emitting an X-ray that is some kind of relatively random amount, and you would expect that the majority of these continuum X-rays are probably low energy X-rays. And in theory, what we kind of see is this intensity of the X-ray emission drop off with the energy as we go up. And one of the actual very interesting things that you can learn from continuum X-rays when you do EDS is the intensity of the emission will go to zero right at the accelerating voltage of the beam. Kind of makes sense. I mean, you can, if you're running at 20 kV, you could potentially create a 20 kV X-ray. And really the case for that is one of your electrons from the beam striking the nucleus of an atom and really just losing all energy in one shot kind of thing. So it doesn't happen that often, but that's something that we call the Dwayne-Hunt limit. And it can actually give you a lot of insight onto your sample. If you ever worry about a charging sample, that's where it shows up first in EDS. You see the Dwayne-Hunt limit, it'll go right to zero, but it'll go at a lower accelerating voltage than the actual beam energy. And that just tells you what the landing energy of your electrons are. The truth is, when you actually look at this in the spectrum, you kind of see this dashed line, you kind of see a hump as it goes up. And really the key thing is, and we'll talk about the window material a little bit, but the window of the EDS detector is going to absorb some of these low energy X-rays, and you're going to see this kind of notch up in the surface. Now, the interesting part of all this is stuff that we really don't care about at the end of the day. So there's tools in the software to really remove this and to make sure it's not part of the quantitative analysis. So again, kind of where do these signals come from? And you know, we got a nice presentation already on the imaging side of it, and using secondary and backscatter electrons to image our sample. And if you look at this schematic over here on the left, what we're really looking at is our interaction volume, if you will. Imagine a cross section here and the electron beam coming down, and this kind of drives the point that, you know, EDS detectors really are not surface sensitive techniques necessarily. Okay, this when you kind of see the cross section here, you know, you kind of see that the first maybe 500 angstroms is secondary electrons that you're going to pick up primarily. Backscatter electrons come from further in; they just carry higher energy. But the X-rays, just being the fact that they're photons and not, you know, electrons, they're going to actually escape from further into the sample. And when I kind of show this schematic, it doesn't mean that something doesn't get created lower. And a backscatter electron can be created lower in the material if the electron reaches that far. It's just that they might not escape to be detected. So this is more of a, what are you actually seeing from a detection standpoint here? But characteristic X-rays always from deeper into the sample. As a consequence, when you come around to EDS mapping, you will never be the same resolution that you could possibly be with the electron imaging. This is the consequence of it. Now, a couple things affect this interaction volume, of course. And one of the biggest effects is the accelerating voltage of the microscope. So what I've kind of shown in this slide is the Monte Carlo simulation. And I'm a big proponent of this program called Casino. It's the University of Sherbrooke that builds this program. But, you know, if you ever kind of have this idea, if anybody ever comes to me and says, well, what do you think the interaction volume is for my sample, and they rattle off exactly what it is, I point them straight to Casino, because it's an easy program to use, and they'll give you the answer in about 30 seconds. So what this is really showing us here is this is silicon across the board. And all I've done is change the accelerating voltage of the simulation. So on my left, I have 5 kV beam interaction, and you can see the interaction volume. There's no electron in the simulation that penetrates beyond 400 nanometers into the surface. When I get to 10 kV, you know, we're starting to push, you know, into that micron regime there. You really don't see much going beyond about 900 nanometers. You can see right away that this is not a linear effect by any means. And by the time we're at 20 kV, you know, 2.8 microns worth of depth in terms of a rough estimate here. I put the scale at 2 microns there in terms of the total depth, so you don't get a good idea of what it is. But you know, it's kind of an interesting effect. I mean, there's this trade-off, because if you look at it from a pure scientific standpoint, you go, well, why wouldn't I do all my EDS work at 5 kV? Because my interaction volume is minimized. I get a better resolution if I want to map it. And the truth is, you don't have enough X-ray lines to play with most of the time. What you're trying to do is you're trying to get out, you know, K lines if you can, which are higher energy lines. You're trying to get out lines that are usually at higher energy, because there's less potential overlap between them, and there's less possible confusion between them. So, you know, generally, EDS is run at the higher accelerating voltage like this at 20 kV, and you just kind of suffer the consequences of maybe a little bit lower resolution. But, you know, in this example of silicon, this is pure bulk silicon all the way down. It's not going to change our X-ray output. This kind of will have an effect later on when we talk about Lair Probe and when we talk about two-dimensional materials and layer structures. But, you know, not for this talk. The other effect that plays in the interaction volume is the material itself. So this is another Monte Carlo simulation, but this time I've just changed the material. So we're at 10 kV accelerating voltage across the board here. We start with a relatively light element like silicon. I know we just saw it on the previous slide, it looked a little different, but I changed the scale just a little bit. So maybe 900 nanometers worth of depth. You go to something like titanium, somewhat heavier, not we're not talking steel or tungsten or something crazy, but the depth of the interaction volume is smaller. And if you want to picture it in your head, I always liken it to the stopping power of a bullet. You shoot it at a it's the three little pigs in a sense. You shoot at a straw wall, it's going right through. You shoot the wood wall, maybe it doesn't go through. Brick wall, maybe it stops altogether. So it's a similar analogy there that you can make. And when we get into something that's maybe a heavier, I don't know, heavier, but more of the engineering material and the nickels, the irons, whatnot, 250 nanometers worth of penetration depth at 10 kV. So materials have a big effect on it as well. So that's kind of, the science. I want to kind of, throw that out there, but I wanted to get into the silicon drift detectors a little bit more. And that's the current state of the art, okay? If the last time you used EDS, it had a liquid nitrogen dewar, or gosh, I mean, if you still use a system that has a liquid nitrogen dewar, it kind of shows how well they hold up, but the technology has really changed. And now we've moved on to silicon drift detectors. And this is just a picture, it's kind of a picture / schematic of our Ultimax. And it's kind of showing you the SEM column, it's kind of showing you the port on the side, so you can get an idea that these things are inserted at a 30 to 35 degree takeoff angle, and we bring the detector in right next to the pole piece, and we only bring it in while we're actually using it. We'll retract it otherwise. So it kind of gives you a good kind of spatial representation of it. But what's it look like at the front end? Because all that matters is right at the nose of the system. And I don't want to drive into all the parts necessarily, but there's really 5 components here. There's a collimator to help make sure that you collect your X-rays efficiently. There's an electron trap. Now, I kind of mentioned it in the slide earlier. I didn't say anything, unfortunately, but anytime electrons reach this detector, it'll register as electromagnetic energy. And so if you get a pure backscatter electron that gets in there that's running at 10 or 15 kV, that could show up on the spectrum. Now, obviously, you got to have enough counts to form a considerable peak, but it's not something that you want in there at all. Electrons have nothing to do with this technique. So we put in an electron trap, so to speak. It's merely a magnet. It's just a means of kind of pulling them out of the circuit. Right behind that is a very important tool, a very important component called the window. And the window is really a vacuum barrier. That's all it is. We want you to be able to constantly cycle the vacuum in the chamber. If you have a load lock, great, but it's not a requirement for EDS by any means. But what we do is we keep everything behind the window under vacuum. And that just makes sure there's no kind of scattering, there's no kind of loss of signal going back. But the problem is that this has to be some sort of X-ray window, and it's a polyimide-based material. So it's going to absorb some things preferentially. It's going to have kind of an absorption edge just after carbon. So, it makes things like, very, very light element analysis trickier. It makes nitrogen analysis a little trickier, but it's kind of a required component for most EDS systems. If you want to talk offline sometime with me, there is a kind of a higher end detector that we make that doesn't have the window in at all. That's kind of designed to look at really light elements, even getting into lithium analysis. And again, don't need to put on my sales hat, but if there's ever a time that you want to talk to me, by all means. And then we have the sensor itself and just an amplifier. And I'm going to talk about the sensor next. Here's what the sensor really looks like. And yeah, we could talk all day about actually how this is prepared. But at the end of the day, I want you to understand where the D comes from, the middle D in silicon drift detector, okay? What happens is you have really kind of a dope material in here. It's really a photodetector in itself, okay? X-rays are going to come in from the top side in the schematic, And what they do is they basically excite electrons and they create electron hole pairs. And all we're trying to do is we're trying to measure the electron hole. Well, you're not measuring the holes, but we're trying to measure the electron count. And we can make an assessment that the number of electrons we generate is proportional to the energy of the X-ray coming in. All right. Where the detectors become kind of interesting is what they do is they build rings along the backside of the detector here. And what that allows you to do is create an electric field within this active area of the photodetector. So you create these electrons and they basically will drift towards the center anode position. And without getting way down the line on detector design, having a small anode in the component allows you to have a much lower noise in the detector. If you have lower noise, you'll see that we'll be able to actually count faster and raise up these count rates. So that's really the design. It used to be the whole back plate with the liquid nitrogen was your anode, and it would just be biased to move the electrons to the back. Now it's a complete drift detector, and that's a little picture of what the detector package actually looks like. This is the full thing. This is actually the window with the actual detector under it and the FET itself. And this is, I believe this was our Aztec detector. So it's something that we even share now in the schematics. So again, I kind of explained a little bit on the capture, but this is the idea. The X-rays come in, they generate the electron hole pairs in the detector, and the drift field is what causes the electrons to migrate towards the center anode. The holes are really just the absence of the electrons, so they kind of migrate towards the front plate, towards the cathode side of the detector. All right. Sorry, I jumped out of 1 second. So what we end up measuring off the back side, off this transistor that we put in, this FET, is a voltage signal jump. And what we're going to try and do is look at something that looks, in a simplified form. It looks like this. There's some kind of amount of ambient noise before, there's an amount of ambient noise after, and there's a voltage event in there. So we're trying to see what was in, what changed, and what we need to do is we need to measure the noise for a certain amount of time before and after to best approximate that voltage jump. Okay. Now, what's interesting is that yellow noise there, or sorry, that yellow band there is your process time. Anybody that's actually sat down and worked on the machine, they're kind of used to these process time 1 through 6 that we have. But basically, a short process time you're measuring for a smaller amount. The number 6 process time you're measuring for a longer amount. And obviously, the shorter you measure, the more inaccuracy you have in your voltage jump. Now, where the detector design has gone for all these years, and this was one of the biggest benefits of having the smaller anode and lower noise, is if you can create lower ambient noise, you don't need to measure as long to actually achieve the same accuracy, the same spectral resolution, if you want to measure it that way. So this is kind of the driving force. If you can make less noisy electronics, you're going to be able to make faster detectors in a sense. It's not quite that simple, but that's really one of the basic points of it. So you can see same resolution, same accuracy if you want to look at it that way, at much shorter process time. That's been the big jump over these years. So that's what we're constantly trying to improve. The other thing that we've been able to improve, if you're used to your liquid nitrogen EDS detectors, was as we've lowered and lowered the noise, when we made the transition from the old lithium doped silicon detectors, that was the liquid nitrogen ones you're used to this SDD model, the noise got so low that we basically went, we don't need liquid nitrogen as a coolant anymore. There might be a way to actually build a solid state mechanism, and that's what we're doing. We have take advantage of the Peltier effect, and really it's just a bunch of kind of alternating PN junctions in the material here, and we just we have the detector on one side, we drive the current through it one way, and we get cooling in the opposite direction. So if you ever see a EDS detector, I'm looking at one right now, in fact, it's got this big kind of bulky back end, and it's a big heat sink just to pull the heat away. But that's how we get it down to the noise level that we want. And fortunately, and if anybody ever did work with liquid nitrogen, no more, pouring liquid nitrogen into a dewar and potentially getting all over, having a potential safety hazard going on. So now it's just kind of automatic. You just take it for granted. But to kind of put a bow on this, to kind of sum it all up, just want to kind of give you an idea what the EDS data really looks like. So you kind of see this animation of the electrons being pulled into the anode here. This is what you see. If you plugged in an oscilloscope and measured it, it looked exactly like this. There's always a certain amount of leakage current that's getting in. You see this voltage build up, and when you actually are generating X-rays, you see a regular jump, and you can kind of see where the noise level is relative to this jump. And people that see this, I presented this a couple of times. This is in some Oxford brochures, and they always look at it and they gotta go, it looks to me like every voltage jump is just about the same. And if you notice that, then you're being sharp. It's really the manganese K alpha that you're seeing in this. This is right off of a test detector as an example. So that's kind of what we're looking at on the end. All right. Now, here's one of the things that's really important in terms of hardware and software is, we're trying to go faster and faster and faster. And you'll hear us advertise we can do 1 million counts per second as an input count rate. But there's kind of a danger here, So actually, it's easier for me to show in the previous slide if I go back. You can have cases where, in this case right here, this big jump looks like it's about 3 times the average jump that we've been seeing. And it's probably the case where at least 2 or 3 X-rays arrived at exactly the same time as the detector. And we just saw the voltage just shoot up. And it's a question of, did I measure this at 15 kV, or did I measure 3 instances at 5 kV? Or it's actually a little closer to 6 now that I think about it in my head. But how do we differentiate that? And this is something I just want to bring up because it's a real source of pride amongst Oxford. We're always worried about this pulse pileup is what we call it. If somebody mentions some peaks to you where you're doubling peaks, that's one component of pulse pileup. But you can have pileup from continuum X-rays, and you can have the spectrum. You can have that spectrum go beyond the Dwayne Hunt limit simply because you're not counting things correctly. And there's a hardware component to all this, but at the end of the day, in our Aztec program, we have a algorithm that's basically designed to work with the quantitative results and kind of circle back and kind of say, gosh, if you have that high of a count rate, and this is the composition of your material, well, then I'm going to have some peaks that I think are in the wrong place. It's almost a predictive type algorithm where it kind of says, gosh, if you look at pure aluminum and you crank up enough current, you're going to double the peaks a bunch, and you're going to have this peak sitting out at 3 kV that's going to be incorrect. And to do the analysis properly from a quantitative standpoint, I need to make sure those go into the right place, into my aluminum peak. And so that's a software component that actually happens in Aztec. And, it helps you make sure that you avoid some peaks, avoid that extension beyond the accelerating voltage, but it makes sure that you get the most accurate quantitative analysis out of the system. So it's kind of important to mention that, going fast is great, but there's potential consequences in it. All right. So just talking about the detectors that we have right now, and there's a couple of I think there's a couple of the Ultimax detectors in the Nuance system here, but what we've done is we build 4 different types of sensor sizes, and just to stop here really quick, the important part about these larger area detectors is they will allow you to get more counts with a larger detector at the same beam conditions all the way across. So what does that mean practically? If I met you and you said, I want to do EDS, and all I look at is metals all day long, this is the case where probably most of the time we can use a higher beam current and not suffer in our analysis, you know. So, you know, you don't necessarily need to have a super large detector in that case. You know, we'd probably talk about hundreds if we were talking about a sales point here. But at the same time, if you had a biological application or something that was very, very beam sensitive, where you kind of said, gosh, you know, if I go above 200 picoamps, I might destroy my sample. Well, you know, in terms of EDS, 200 picoamps with some of the smaller detectors, it's going to take you a long time to do spectral analysis. You could be there for a couple minutes to do one spectrum. So the idea there is, let's get a larger detector so we can get everything we possibly can out of the case, you know, because you're going to be material limited in that case. So that's why, you know, that's why we kind of brag about these really large detectors, and that's where the real benefit actually exists. And they kind of work across the board the same way. So the other thing we couple it with is the Aztec Live software. And again, I think there's a couple systems in the center that have the Aztec Live capability, but this is something that is really a driving force for Oxford now. It's really kind of the state of the art, so I wanted to kind of mention it really quick. This is a pretty good video here. It's looking at an additive manufacturing powder, and what's the expectation was it's expected that this is a titanium powder. But what we're looking around for is contamination. So we've turned the titanium on in blue. And then we've noticed that, gosh, you know, all the particles show up and it looks like we have a tungsten signal. So we've turned the tungsten on red. And what we're really interested in is this gray one that just showed up. And it's like, well, what in the world is that? And when we actually do our analysis on it, we find out that that's a nickel particle that's buried in it. And, you know, all of a sudden you realize that, you know, this great additive manufacturing pure powder isn't exactly as pure as we thought. And rather than trying to hunt around and find the nickel particle in the haystack, so to speak, we've just found it by driving around and taking advantage of the Aztec Live capability. So this is something that can really be beneficial if you're looking at something completely blind. If you kind of go, I've got an idea where to look on this sample, but you know, who knows? I guess I skipped over something there, but the other thing that we wanted to kind of press with the Aztec Live capability is the old way we used to do things. Imagine, you know, the electron image that we have on the left there, and you know, maybe you went through and did this nice job of stitching together multiple fields, so you really have a great overview from an electron image standpoint. But historically, when you did EDS, you'd kind of pick and choose different points. You know, here we have 5 different points, all very interesting on their own, but is it telling you everything you need to know about the sample? And what you can do is, you know, again, the animation there is just showing me kind of the individual pieces, but you're missing, you know, you're kind of missing the gaps in between, so to speak. You know, so do you really have an idea of what the big picture is? And this is what we want to do with Aztec Live. Is there could be situations in here as you drive along where, gosh, you know, this whole kind of yellowish green area, it's all kind of the same. You know, it's got kind of its highlights, but you know, if I captured it in one location, I'd kind of have the big picture there. But at least you're connecting the dots, or you're seeing transitions to different phases. So there's no gap in the information that you collect. So you're really getting a better idea of what your sample actually looks like. We don't want the fragmented data anymore. You know, this is where, you know, the last thing I wanted to talk about really quick was just going into the actual basics. Kind of how we get from, well, sorry, you might start with the Aztec Live, and at the same time, there's plenty of people who go, I know exactly what I'm looking at. Like, I just want to go directly to the sample. I want to get some information. So I just wanted to kind of mention where some of this information comes from, how the X-ray mapping really works. And X-ray mapping is probably the starting point for most people in this case. So it's an actual beam raster where we're actually picking up and digitally moving. We're not scanning across the sample here. But what we do is we just simply say, you know what, the general EDS spectrum of all the points that we've gathered suggests there's some silicon there. So I'm going to create an energy window around my silicon peak, and preferably a higher energy peak because there's less overlap with other things. But you see, create this energy window for silicon, and then what we're doing is we're storing the information at every single pixel. So where there's a higher peak, there's a stronger point in the X-ray map. Okay. The real reason that we do X-ray mapping first, or why it seems to be predominantly where we start with things, is the mapping is a hyperspectral cube. You kind of go, again, all it means is that every single one of your data points has a spectrum associated with it. So if after the fact, heck, it could be 5 years from now, and I've done this on samples, what am I looking at in this bright spot over here that seems to have a lot of silicon right here? And you could go and extract the actual spectral data from that and look at a spectrum of it. This is something that a lot of users like to use in, like freeware imaging software, ImageJ, ListPix, stuff like that. We can export the raw data cube if that's the way you want to look at your information. So when you look at mapping, how do you want to set it up? You want to look at something like this iron map here, and you want to be able to see that it represents the sample. It's showing you this distribution of percentages and whatnot. It's revealing small little differences. You can kind of see the little red arrow showing me there's little inclusions here and there. It reveals the real small features. Those are little magnetite inclusions in this granite sample. And it's really achieved by predominantly high counts. So when you come in to do your mapping for EDS mapping, the real big trigger is get as many counts as you possibly can. The idea of, I kind of showed that schematic of the voltage and the noise, and the consequence of a short process time is a little bit more inaccuracy. The spectral inaccuracy that you're going to suffer is not a big deal when it comes to mapping. You're trying to look at something graphically rather than being an exact number of how much something is there. If you want to know composition, yeah, there's such a thing as quant map, but the real detail is when you extract the spectrum or you actually go do your quantitative analysis. So the last thing I wanted to talk about, and I'm going to try and hustle through this, I want to be respectful of time, but where do the numbers actually come from here? And it's really kind of a 5-part step. You acquire this spectrum, you remove our background X-rays there, and we do a top hat filter to get rid of it. And then we look at peak deconvolution. So we have to worry about cases where there's overlapping peaks, the nickel, the cobalt, the iron down here. How much is being contributed to this peak from each one? The bonus here is that each of this iron, cobalt, and nickel all have higher energy peaks that don't have any overlap on their own. So we can actually use that to do the math. But when it comes to lower KV, that's where it gets a little trickier. Or when it comes to light elements, that's where it gets a little trickier. And then all the math is compare the net intensities for your peak, so the chromium in this case is highlighted, to a known standard. And Aztec has a database of standards, so it's all in there. You don't have to necessarily create your own standards, although you could, but you have a database available to you, so you're just comparing to that. And then you have to do the magic kind of matrix effect correction. And I said magic, but I kind of regret that I just said that. But what we're adjusting for is everything else that's there. Chrome by itself is going to have a different X-ray content than if it was chrome with cobalt, nickel, iron, titanium, moly. So all the other elements there have an effect from the standpoint of absorption, the stopping power of the electron beam, potential fluorescence. So that's what I'm talking about when I talk about matrix effects. But at the end of the day, I put this in here, I kind of say it's a simple formula, and it's with a big kind of question mark, kind of quotation mark if you want, but it's really the measured intensity of your peak against the intensity of the standard. And then we run this through our matrix correction, which is a pretty high level algorithm, obviously. And that will give you the ratio of your unknown element and your known standard there. So, you know, going into it, there's a lot of engines in the Aztec software that kind of make sure that we do this right. And I don't need to get into all this. This is a bit more of a sales pitch and all, but you know, the one things that I do want to bring up is that pulse pileup correction is very, very critical to getting things right. And then using the other tools that we just have confidence in. So that's what this QCal, FLS, XPP kind of has to do with. So the normalized slide here, I'm going to talk a little bit more about Lair Probe when we come up a little bit later. And normalization will be something that we kind of talk about in that. So I'm going to kind of leave this slide off and just mention that there's 3 major requirements if you want to do good quantitative analysis, okay? What we want to do is we want to make sure we have an homogeneous sample within the interaction volume, okay? I'm not asking the whole sample be homogeneous, that's impossible. What I mean is there's an assumption in the software that where your beam's interacting is one homogeneous, you know, composition. And that's how we do the pulse pileup correction correctly. That's how we do the matrix corrections correctly. And if you don't have that, then basically you can't take a lot of accuracy away from your quantitative analysis. There can be some assumptions made. There can be some generalizations, some comparisons. But in terms of high accuracy quantitative analysis, be careful. The other part is a polished surface and just a flat surface. We just don't want, you know, helix on the sample or particles blocking X-ray paths to the detector. And the last part, and this can be important, but it's not the end of the world if it's slightly non-conductive, but conductive samples is an important thing because you can actually have the case, we talked about this Dwayne Hunt limit earlier, but you can have the case where you're completely landing at a different energy than the software thinks. You know, the software says, I'm reading 20 kV worth of accelerating voltage. So that means I can use all these high energy lines. And truth be told, when you look at the spectrum, the Dwayne Hunt limit's at about 10, and you got a huge cloud charge or electron charge on the surface that's screwing up the landing energy of the electron beam. And in that case, you might pick the wrong lines for quantitative analysis. So those are the 3 things that I always bring up. I always kind of stress to users, if you want to see good quantitative results, those 3 things will help you get there. And then I just leave it open for questions at this point. So Tirza, if there's any questions at this point, or we can move on.
Thank you, Mike. So we do have maybe a few minutes for questions. So, and then we'll take a quick break. So you can raise your hand. You can put your questions in the chat. And if not, we will move on to the break. So I'll just wait a minute for questions to pop up. And for everybody that's watching, the second part of this morning session over Zoom will include live demos from our microscopes. So both Muto-san and Mike will be on the SU8030 doing demonstrations on both STEM, scanning transmission electron microscopy in the microscope, and Lair Probe on the Aztec software. So if you have a question, go ahead and type it into the chat. We have one person that's going to type out a question. So Mike, just be ready. I'm not sure how long it's going to be. I can read it out loud as well if you'd like. But, we'll take this one question and then we'll move into our 15-minute break. And then after, or at 11:15, we'll get started again. So we'll just hold on one second.
What's reasonable magnification for EDS? That one?
Yes, so there's one so far. Yep, it just says, what is a reasonable magnification to use for EDS?
So it's a really good question. And there's no magical answer to this, but I would say, you know, a lot of people like to do mapping at really, really low magnification. And if you've ever tried it, it usually works fine, but there's a little bit of a kind of a consequence. And if you look at the corners of your maps, you'll notice that if you get to really, really low magnification, you're actually deflecting the beam so far that you're actually out of the kind of the preferred geometry for the EDS detectors. So you'll just see a drop off in counts in the mapping side of things. So for an individual map, probably no big deal whatsoever to go to the lowest magnification you can get to. If you ever were to stitch together maps and you were to do like a whole large area, you'll see that effect really jump out quickly. When you talk about quantitative analysis, that's where I want to be at higher magnification. I would say if you're not kind of in the center of your field of view, you know, then you want to be at something closer to about 1000x or even 2000x to make sure that you really are not losing any count rate across the entire sample to do good quantitative analysis. Should we take the last one too?
Yeah, if you have any questions for our Muto as well, please put them in the chat. We do have a few more questions, so maybe we'll take one more. And then we can answer the rest later. I'm just looking at the questions right now. So there's one about spatial resolution, but I think that one of the questions that we get a lot here is what if your sample is not flat? How can you get the best EDS results and not, I guess, non-quantitative elemental information? So we do have a lot of people that do EDS on materials that are not flat. So I think that would be a good question to end on, and then we'll go into the break. And then again, please put your questions in the chat after that.
Sure. So to me, would be with something that's not flat, I tend to think of the mapping a little bit more, and at least that gives you a kind of an understanding of the material. You know, it gives you kind of the basics of the composition, and the only drawback on the non-flat is shadowing effect in that case. So as long as you're not willing to take it for, you know, a really high-end quantitative result, you know, take the mapping and don't worry about the shadowing so much. And you know, if the shadowing is a big deal, most SEMs nowadays have ports on the opposite side where you could accommodate a second detector if you wanted to go that far. So, you know, there have been a few customers of ours that'll put 2, even 3 EDS detectors on to make sure they don't miss anything around the entire particle in that case. But yeah, if it was a quantitative thing, the best you can do is to try and kind of hit straight on the top of a, you know, if it was a spherical sample, try to hit straight on the top of the sphere, or try and hit on the flattest part. That's about the best you can do in that case. But you know, just don't take it for a really high quantitative or high accuracy quantitative result.
Then just real quick, because I don't want to cut into the break too much, I just wanted to follow up with a question that was also brought up, and we get a lot as well. So if you do a map on a rough surface or a flat surface and you find an area where there's a higher concentration of a certain element, is it better to do a point and ID analysis there, or should you do another type of quant map or something else like that?
No, if you wanted to do anything compositional, I'd come back with a point and ID kind of thing.
Thank you so much. All right, so please put all your questions in the chat, and we'll try to get to any of the questions that you have for either Mike or Muto-san. So keep adding them. We're going to take a quick 15-minute break, and when we come back, we will be on the microscope. So we hope to see you all back here in 15 minutes. All right, welcome back, everyone. I'd like to reintroduce Atsushi Muto from Hitachi High Technology, who's going to give you a demonstration on scanning transmission electron microscopy in the Hitachi SU8030 SEM. So thank you. Take it away, Muto-san.
Thank you very much, Kaza. So I hope you can hear me. Oh, it's working now. Oh, yes.
We can hear you. Thank you.
Oh, okay. Thank you very much. I didn't know that. Thank you very much. So, yeah, thank you very much for the live session. Before going to the live session, let me quickly review the STEM function side. Yes, as it will be for some people, it will be a first time. So, yes, yes. So this is the agenda for 45 minutes. If time allows, I'd like to touch to the deceleration function part. Yes, but let's focus on the STEM at first. So this is a STEM yes, deceleration and STEM system overview in the optics. So we have a STEM detector and the STEM aperture. Where is the STEM detector and aperture? Just yes, just in case you can find. Yes, I just show the image of the nuance centers SU8030. So in addition to the STEM detector, nuance centers SU8030 has a STEM aperture. So that will increase the contrast to get the better image, especially for the nanomaterials. So I will show how to use that and what the benefit is in life. And yes, also yes, a safety part. Once we set the STEM detector, we have two restrictions about operation. So stage Z, yes, stage Z is we cannot set no longer than 20 millimeter, and the stage tilt is also no higher than 10 degrees. This is automatically detected by the software systems, and the user interface is automatically restrict the range. So your user side, you have nothing to do. Yes, but why it happens, I'd like to quickly explain. So I'm showing the optics information, and actually STEM holders, below the STEM holder, we have a STEM SEM stage. Actually, SEM stage, we have a hole through the yes, hole, yeah, a hole to yes, introduce the bright field signal. So, and below the stage, we have a detector. So yes, if we insert the detector, of course, these detectors and apertures are below the SEM stage. So this is why if we'd like to go lower or tilt, there's a potential to hit. This is why we are limiting the Z and the tilt. So if you enjoy the STEM imaging, please retract the STEM detector to the original position so that the next user would like to tilt the sample and would like to see the bird's eye view, but we cannot do tilt. That happens. So, and this will be, I think, many people, so first time to see the STEM holder. So STEM holder is, yes, this is yes, we have a two, yes, a STEM film sample, attaching area, fixing area, placing area, and the conversion plate to detect the DF STEM signal. And the center part, we have a hole, a through hole to introduce bright field to the yes downside. So how to set the sample? Yes, I can demonstrate, but it's a too tiny structure, so I'm just showing in two pictures. So hopefully you can easily understand. We will just loosen the top screw and just slide the top holder. And you can see the recessed area at the center, top center to yes, hold the yes, TM mesh or any type of the TM yes, or FibSem mesh. So yeah. After placing the structure on this area, this is a 3 millimeter diameter. Then yes, slide back the top holding structure and the screw, and we can hold the sample. And also these yes, reflection plate is making a roll to yes, detect yes, receive the dark field, high scatter angle, highly scattered transmitted signal, then convert to the secondary electron. This signal is detected by the lower detector, lower chamber detector. And yes, if you are familiar with the STEM imaging, yes, maybe that's a question. High angle annular dark field. Yes, high angle work can be done. Yes, we can do by just replacing the plates. Yes, with larger hole. In larger hole structure, yes, we don't take the yes, small angle part and getting more high angle side. So we are, yes, we have two types of the hole structure, but you can imagine if you have a 3D printer technology, yes, you can kind of the design and make any type of the yes, unique type of the yes, detection yes, structure to detect specific angle. So that is possible. One advice when you manufacture by the 3D printer, so please coat the gold on surface using the spatter coater. Yes, so we are making gold plating to improve the secondary electron emission when the scattered electron hits. That's a kind of the point of the yes, yes, if you'd like to go further. And also, yes, in the previous session, yes, some thought is how small features we can do mapping. Actually, if you can prepare the sample in the STEM, we can maximize the performance of the mapping spatial resolution capability. So currently, we are just getting this is a one generation older tool of yours, and we are using the EDS detector one generation, not older, one generation newer one. This is an example. So we are seeing the 20 nanometer ion structure. And just observing the mapping by the Aztec system. That's also, one generation. No, I think, so almost similar resolution, similar generation data. But yes, we are doing the mapping for the 20 nanometer. So yes, mapping procedure is, I think you all are familiar with the Oxford Aztec software system. So yes, we'll set and do mapping. And we have a small delays, but the point, if you'd like to try an EDS mapping in a STEM sample, you have to be little patient because the signal is not, we don't get so many signals. So yes, kind of using the stable state, stable beam condition, and wait for maybe 10 minutes or 20 minutes patiently so we can detect the signal. Get the EDS mapping, so you can see the ions distribution. So the result is like this. So we can take care of the 20 nanometer of this different EDS system, but and also one generation newer SEM, but we can do 20. And if you'd like to go beyond, for example, this is 500,000 times 8 nanometer and 5 nanometers ion particles. So yes, also this is a mapping trial using the Oxford Aztec system. Also, this is a kind of using the little special detector. But yes, you can see 8 nanometer and 5 nanometers. Ion is gradually getting mapped. So that's a kind of the benefit of the STEM system and the EDS combination. So yes, I think this is a live session. So let's run further through the live operation. So yes, is it possible to change to the user interface to share? Thank you very much. Okay, so yes, so I just set a sample. A sample setting is quite same way as a normal sample holder. And sample is now inside. And what I'm going to do is setting the condition. First, let's set the condition accelerating voltage at 30 kV. So beam can penetrate or not penetrate. This is the most important point for the SEM STEM imaging. So let's start from the 30 kV. And other conditions, you can keep as a normal defaults like a high mode, condenser 5, and starting from the secondary electron detector. That is okay. So what I should do is starting from the normal SEM operation. So give me 20 seconds to be ready to get the beam, get the image. Yes. So first, I will get this is a TM grid. So also for the TM STEM imaging for the SEM, one of the good tips is appropriate selection of the grid, TM grid. I prefer to use this lacy carbon grid, lacy grid. So we have a kind of the holy structures. Yes, sometimes yes. If the like a material like carbon nanotube can go across this kind of lacy structure, we have a good chance to get the good penetration without interacting with these base materials. So we have a better chance to get yes, kind of a good data. So what I'm currently doing is, as you see, yes, beam alignment and aperture alignment. Sorry, I should align before, but yes, so I apologize to show my, yes, operation, yes, normal operation part, but yes, that's what I'm doing. Yes. And if you think it's okay to get the focus and the streamer collection, yes, it's quite easy. You will move to the something area of interest to see the structure. Yes, let's observe these kind of the, yes, a little aggregated part. Then what I should do is to changing the, yes, a signal selector at the right side of the tab. Here, where you can select the TE. So normally, yes, it happens, yes, lots of signals to saturate. So please don't worry, select ABCC, and we can see the data. So this is a STEM image. And so just let me check the condition. So if you'd like to capture the image, now you can see the inner structure, including the, yes, metal. I think that will be used for a catalyst. And yeah, inside the tube, yeah, and you can see the tube structure as well. So yeah, if you are familiar with the SEM operation, honestly saying it's quite easy. So, and if you'd like to get the secondary electron and the STEM image at the same time, so you can select these scan side selection box in a SEM side to dual. If you select dual, we can show two screens. And which one, yes, I will select in which screen. So you can select the signal selector A, takes care of the left side. Signal selector B takes care of the right side. So, and if you now currently, I am changing the, yes, getting the T STEM image at the left side and the SEM image at the right side. Yes, and we can select the, we can capture the image. We can capture both images at the same time. So good point of the second, yeah, SEM image, it's, yes, by using the SEM image, we can see the topographic information, which is, yes, a higher, yeah, locating a higher position than others. So this topographic information will be helpful to understand the, yes, features and, yes, sample situation. Yes, so that will be a good, yes, good point. And also, yes, I said, yes, yes, this SEM, this, yes, a sample holder has a dark field imaging capability. So let me show that. So I will just focus back to SEM. Okay. So if we'd like to select the dark field image, we'll just select the secondary electron lower. SEL, now secondary electron chamber detector is detecting the, yes, scattered electrons, yes, scattered electron, secondary electron signal. So as you can see, so now by this way, we can get the bright field and the dark field at the same time. So dark field image is kind of similar to the backscattered electron image. But yes, if we try to get the backscattered electron image in this type of the thin film sample, it is a big challenge because the backscattered interaction is very rarely happen in such a thin film type samples. So it is more reasonable to utilize the transmitted signal, scattered transmission signal, to use the dark field to get the image. So yes, if you are familiar with the STEM imaging, bright field, you can see almost the same information. we can get the similar information in a bright field, and but the dark field is more focused on the composition. Okay, so I'm just wondering up to this point, do you have any questions? It's fine. Okay, so next is normally if you'd like to see the STEM, you'd like to increase the magnification and see the fine features. So I would like to show how some tips how to get the high resolution image. First, working distance. So our sample holder is set to work at the 8 millimeter at default, where we just set the sample. So let's change the working distance a little shorter if you'd like to get the better resolution. So how short? Just 6 millimeter, 2 millimeter up. That is good enough. And the next, what we do is, let's make a stage lock. So this stage lock is a function to kind of giving the additional extra stability of the stage. Once we set the button, a sample is moved, but if you wait for a while, stage becomes very, very stable. And very strong against vibration and acoustic noise. I'm happy to operate in this nuance center's room. It's a perfect circumstances, but that stage lock will give the additional extra help to get the stable image. And the next is SEM side. Please change the probe current mode from high to normal. Actually, currently I'm using the normal. Yes, if you use high mode is I think normal condition. Normally you are you use for the operation. High probe current giving the lots of current to give the more comfortable operation circumstances, but losing the resolution. Actually, if you'd like to maximize the resolution performance, please select the normal mode. Normal mode is stronger condenser lens excitation to kind of the more focusing on resolution settings. And after moving, after setting the and the next is alignment. Yes, if you'd like to do alignment, we should use a TM image or SEM image. My answer is the SEM image. Please use the SEM image to align the beam and aperture. So let me do additional beam and aperture alignment. So TM, if you project a TM image and trying to align this aperture alignment, so image behavior, wobbling behavior is a little different, and that makes a confusion of the operation. So yes, it is good to think, operation, alignment operation is better to be done by the normal SEM image. Yes, okay, I make it. And now, yes, what I'm doing is now I'm seriously, aligning the focus and stigma. because yes, this static heavy condition is the highest imaging condition. Any small mistake of my focus and estimation will be, yes, very clearly highlighted in my, yes, output. So now I just, yes, align the beam and, yes, focus. Then, yes, I will move to the some of the area of interest. And changing the one of the detector to the stem. Maybe I think I will set it to this stem. And align the secondary electron signal. And capture the image. Yeah, thank you very much, Nuance Centers. Yeah, excellent imaging circumstances. I'm sure I can show the best performance here. So now you can see the small ion particles and ion particles inside the, yes, nanotubes. And the large nanotube and the small nanotube. Even in the small nanotube, you can see the small also, yes, particle structures. And secondary electron image, sorry, it's a little, yes, saturated, but yes, for example, only TM image, it is very difficult. These small nanotubes are how small nanotubes are interacting with large one. So now secondary electron image clearly shows how, yes, they are interacting. So I hope you can, yes, enjoy the, yes, very sharp and very nice imaging of the stem, yes, by this way. It's very simple. And the next is, yes, to get the better image of this sample. So I hope you are happy with the current image quality, but SU 8030 stem function can do better than this. So what the trick is a stem aperture. Yes, we have an aperture function that is optional accessory. So if we set the aperture, what I'm doing is inserting the aperture structure to the, yes, chamber. So you can see image becomes very dark because I set the very small apertures above the detector. So yes, it makes sense. Some of the signal is cut out, and this is why, yes, a signal is yes, becoming weak. But the benefit is resolution. Resolution itself is the same, but the contrast is very well improved. So now we start to see more. So I will just capture the image and show the difference. So after, yes, now I insert the aperture and get the image, and let's compare the quality. So you can see by inserting the aperture, for example, if we focus on a smaller tube area, we can get more, yes, information, yes, internal information. But large tube area, actually we are losing more information. Yes, so stem aperture can increase the contrast, especially for the very thin sample area, but thick sample area, penetration more sensitive to the sample thickness. Thicker area, we are tend to lose the information. Yes, so that's a pro and cons there, but yes, if we utilize this aperture, yes, I'm sure we can get the very nice quality image. Yes. So I'm just going to the, for example, yes, small structures. To get the image. And also, yes, to get the best image, yes, of the stem. Also, one of the point we have to be careful is sample contamination. So image looking good, but currently what I'm seeing is hydrocarbon deposition. So maybe I think to make it easy to see, I move to the, yes, small structure area and doing the reduced area. So you can see structure is becoming, yes, thicker and thicker. So if you zoom out and going back to the secondary, you can see the sample hydrocarbon is deposited, and that will kind of that becomes a very critical, yes, a limiting factor of resolution. So yes, I apologize, I didn't clean up the sample, but before setting the sample, yes, some preparation to degas the sample. In case of this type of the carbon nanotube samples, normally what I do is put the, yes, a grid on, yes, a heater, and stay for maybe, yes, stay at 100 degrees Celsius for maybe 10, 15 minutes. By this way, normally we can remove that, yes, a contamination source. Yes, again, in summary, yes, we can operate as normal SEM operation, and just selecting the TE, we can detect the, yes, a TE image. And by selecting the secondary electron lower, we can detect back, yes, dark field image. If you'd like to align the brightness and contrast of each screen, you can select image adjust A, B, radio button. That button is corresponding to the which side to your manual adjustment will work. So yes. So yeah, I'm sure if you have any kind of the sample to try, yes. These 2 days, yes, yes, Mike Oxford and I are working with Nuance, yes, engineers. So yeah, please take advantage of the opportunity to bring the sample and let's observe the stem sample together. So yes, I have 10 minutes and will be a little challenging to go to the deceleration. But first, do you have any questions about the STEM operation part? Okay, if not, yes, I will quickly set up the, yes, I take out the sample and set the sample for the deceleration, and hopefully I can show how to do that. Okay, so currently I'm taking out a sample, and in the meantime, Taza, is it okay for me to grab the screen back to the, yes, to quickly, yes, review the deceleration function. Thank you very much. I'll go back to my screen. And yes, so deceleration. Yes. So deceleration is a technology to apply a bias on the stage. So in this case, normally we can, yes, get the better resolution. Yes, we can start from the high accelerating voltage. So that will give us the less chromatic aberration, yes, optics, and can give the better resolution. Actually, deceleration technology works at, especially improve the resolution at the low accelerating voltage field. And this is a kind of the routine, operation workflow of the deceleration. Normally, I am not starting imaging using the deceleration mode. First, normally, I'm using the normal low voltage because, the system itself is also without deceleration, having a very high resolution. But yes, at high magnification, if I'd like to get a better resolution, yes, I will set the deceleration. So again, deceleration voltage, yes, accelerating voltage minus deceleration voltage is real landing voltage. So yes, we can start from the 3 kV and decelerate to the 500 volt. In this case, we can get a better resolution. And why I don't use deceleration for all samples? Instead of the lots of benefit and advantage, deceleration has also tough part, some disadvantage points. So this type of samples, sample locate, deceleration field to get the best deceleration image. We have a one rule. So deceleration field formed by the specimen, I'm showing in the right side diagram, and the primary beam have to make a perpendicular relationship. So if the sample is tilted, or if we'd like to observe cross section, or sample structure is really rough, so this deceleration field is not formed perpendicular to the primary beam. So in this case, it is very tough to correct the stigmation and the focus. So one of the case I frequently receive the question is, cross-section sample imaging. So cross-section is completely impossible. My answer is yes, no. We can do the cross-section imaging. So normal cross-section imaging sample is sticked out from the holder, and that edge is making the very strange deceleration field. But if we set a sample, for example, flash to the sample holder, we can make a static deceleration field stable and perpendicular to the beam. So I'm just showing the one of the example using the cross-section holder. I'm setting the cross-section sample to the holder and close to the edge. I'm just align. We have a better alignment way. We have a jig now, but showing the ideas. And by this way, we can make a flash to sample to the jig and can observe the sample. Recently, a 3D printer technology can let you do more flexibility to customize sample to fit with your needs. So hopefully, that kind of idea will encourage you to try the deceleration technology. So I hope I have 4 minutes. So Taylor, is it possible to get back the screen to SEM user interface side? thank you very much. And I am going to see. Okay, so I'll go back to secondary electron image. And let's set 800 volt. And the secondary electron to the ABCC. So what I'm observing is a mesoporous silica structure that shown in yes, slides. So first, let me try to get the image without yes, deceleration. So also, yes, it's a little serious charge up is here, but we are expecting to see the kind of the yes, porous structure in a silica surface, but due to the lack of resolution, it is very tough to see. So if you'd like to use the deceleration, what we do is first select the deceleration checkbox. Then select the yes, deceleration voltage settings. So high and low and free. So if you become familiar, you can use the free, but yes, this high and low controls the deceleration voltage. Yes, so voltage is high, we can get the better resolution, and the voltage is low, we can get the yes, better flexibility of the yes, kind of the sample. If the sample is not the ideal situation, we can get the image. We can get the image if you set to low. So after setting the deceleration, so what we do, what we should do is quite same as normal. So just focus and the stigma correction. And now you can see the yes, fine porous structures. We still see the yes, charge up, serious charge up, but also deceleration has a good function to take care of the charge, reduce the charge up by changing the signal mode. So that will help you to kind of take care of the also non-conductive sample. Okay, so and now I realize it's my time. Time is finished. So it's around yes, it's a time. So yes, so if you have any questions, yes, yeah, please let me know by text or later. Yes, by email or anything. So and I will try to respond to you as soon as possible. So okay, thank you very much.
Thank you so much for the wonderful demonstration. We're gonna, if you have questions, you can put them in the chat. Also, if you have registered for lunch, you can also talk to everybody at lunch. So we're going to move along and get things set up for Mike and show you some EDS. So just give us a moment and we'll switch over.
Yes. Yes, sampling. So let me move the sample. Oh, sorry about that.
Okay, I think I'm ready when you are. Hear me okay? Off tower.
We can see your PowerPoint very well, and so just let me know when you're ready to switch over to the screen share, and I will do that for you.
Okay. Are you? Can you hear me at least?
Yes, I can hear you very well.
Okay. All right. So I'll get started on my part here, and yeah, I'll let you know when we switch over. I think we're almost set on the microscope side anyway, but yeah, I wanted to introduce Lair Probe, and this is real interesting tool that can be really helpful for probably a select few that may be joining the call today. So it's a tool that we developed for determining composition and thickness in two-dimensional materials using the EDS. So just what I want to do is kind of give it the basics, kind of understand, you know, what we're doing, how we kind of go about it. I have two examples. We might not get to the second example. I want to kind of keep with time today. I'd rather show you the live demonstration of a 3-metal deposition stack and kind of show you the process flow on that. So I'm going to move to the presentation here, and I want to kind of start you in the bulk EDS where we did the presentation earlier, but we're going to move out of that really quick. So, you know, EDS work on a bulk sample, you know, we're really looking at, you know, specific points in the region. We're you know, identifying the spectrum, but we're basically looking at it going, everything that shows up in this spectrum, you know, in this example, the calcium, oxygen, silicon, iron, is all expected to be in the same interaction volume there. And so we can kind of say right there, you know, we know we have this mineral, and gosh, if I could remember exactly what it was, I feel like a geologist again, but not a geologist at the same time. But here's where things kind of get a little bit more complicated, a little bit more muddled. And what we've done is, you know, with the better microscopes, with the better EDS detectors, you know, we've started to be able to do some real interesting things. And this is an example of the upper portion is a 3.5 kV setup here, where we're basically looking at an aluminum matrix. But we have these regions here, and you can kind of see the bright region in the bottom right, the kind of reddish region, that's just your aluminum. But then there's these flakes here in green that are, you know, to some extent, we know there's some kind of form of manganese, iron, and silicon. And you can put the spot on them, but the truth is, these are really thin flakes on the surface of the aluminum. And when you look at the spectra, you're always going to get an aluminum peak in this case. And it's really because in your interaction volume, you don't have an homogeneous sample anymore. So looking at this, it becomes very qualitative, and there's no quantitative side of it at all. I mean, we're looking at it and going, yeah, it looks like there's a difference between this flake and the matrix material, and that it's comprised of manganese, iron, and silicon. But if you read our quant results, it wouldn't make any sense because of the aluminum. And it even goes all the way down to 1 kV. You can start to, you know, really try to isolate out the flake itself, but you're always going to have the aluminum in it. So, you know, basically, you know, we have this means of doing kind of the analysis that's non-destructive, and it kind of shows us what the flake is comprised of. But, you know, what we really need is a way to isolate the flake and to kind of say the flake is, you know, so thick and comprised of this material, or sorry, the composition is, you know, such and such. And really where the problem exists is in the interaction volume side of things. You know, here's a problem that comes up in nano devices a lot. It's very similar to this flake analogy that I was kind of starting the presentation with. But, you know, if you looked at a material in a nano device here, when you analyze maybe the source in this example, you're going to get a lot of information from the source, but you're also going to get it from the buried dielectric. You're going to get it from the gate material. When you go to the drain in the other source, you're going to get mixtures of a bunch of different materials. So the fact is, you kind of go, I don't know what's coming from where, and this is what we hope to kind of sort out. And this is what Lair Probe is doing. And, you know, again, there's a Monte Carlo simulation here to kind of help visualize what's going on. But this is not necessarily something that's in the software. But what Lair Probe is designed to do is to give you the composition and thickness of multiple film layers. And you could do one layer, you could do up to 7 layers if you wanted to. And what we kind of expect in the typical thickness range, hundreds of nanometers, but it could be all the way down to 1 or 2 nanometers. I mean, there's examples, if I have time, and again, I might run out, but there's examples where we've detected monolayers of like moly disulfide in samples. So there's a lot of potential here, but it does require a little bit of effort to go into it. So, how's the process flow really different from a regular EDS spectrum? It starts with you defining a model. So we need some kind of guess. We need some kind of starting point to know how to know what our film stack looks like. And that's what we input on the described model step. After that, it largely looks like the regular process flow in Aztec. What we do is we kind of set our analysis conditions after that. And this is the type of thing where, if you have a film that's, 5 nanometers, it's kind of silly to run something at 20 kV because you're just going to blast through your whole thin film and you're never going to really get enough signal from it to do a good job. So the system is designed to kind of give you cues or to kind of take your model and say, hey, this might be the best operating conditions for the microscope in terms of accelerating voltages and where to set the EDS range and channels, things like that. After that, and this is where it's critical, and this is where it's actually different from a lot of EDS analysis, is you have to measure probe current. And in Aztec, I think people immediately say, oh, you need a Faraday cup, and that's not the case anymore. Faraday cup is not what we do with Aztec. What we're actually going to do is we're going to use an optimization element. And the optimization element you should think about depends on what accelerating voltages you kind of plan to use. But basically they're pure elements. Silicon's going to make a good one, copper's going to make a good one. But basically we're going to do this probe current measurement on a pure optimization element. It doesn't have to be a standard, just has to be pure kind of thing. We're looking for K lines and that, and I'll try to explain this more as we get to it in the software. But then this goes to what you're used to. Get an X-ray image, or sorry, get an electron image, get an X-ray spectrum. And then what we're going to do is we're going to take the spectrum and we're going to plug it through the model and determine what the composition might be, what the actual thickness of the layers might be. So kind of an example going through here with a nitride and an oxide layer on a silicon device. You can have multiple unknowns. You could have unknown composition and unknown thickness in the system, but basically the model helps kind of set up a framework of what at least your first guess is, so to speak. And here's the example of what it might look like in the table at the very end, where a single spectrum, you're going through it, and what you actually have to do in this case is kind of select which lines you're going to use for the analysis. So maybe there is a little bit of a learning curve to it, but it's something that should be sensible. There's some really good simple rules that we can pass along to people that are going to be interested in this. So how the measurement works, and this is where I got to bring in some terminology and make sure everybody's kind of understanding what we're talking about here. So in the earlier session, I kind of showed the ultimate equation for composition calculation, and it started with the relationship of the intensity, the X-ray intensity of your unknown versus some kind of standard. And that ratio is something we call K ratio. And K ratio is basically at the heart of Lair Probe here. So we're going to use a bunch of K ratios effectively and try to minimize minimize the difference between your measured K ratio and what's predicted. And so, if you just did a single film on a substrate, if it was one layer, you could actually plot a calibration curve. You could just watch the K ratio change versus thickness. And then you have your calibration curve. Why run Lair Probe every single time kind of thing? You can do it once and be done. But where it's really where it's really promising is actually multiple layers and multiple elements at that, and trying to do kind of a forward prediction of the K ratios. And this is something that has really been, it was originally kind of proposed by Puchu back in 1993. If that name sounds familiar, he's one of the P's in the XPP matrix correction, if you're familiar with it. But that's kind of at the heart of all this. We're gonna basically use that model as a starting point for a predictive K ratio. So quick example here. You have maybe two unknowns. Let's just say we have two films that are, different thicknesses on a sample, just to give you kind of an idea how it's going to play out. What we do is we measure the intensities of the elements, and then we convert that to K ratios. And we have an initial guess, like I was saying, for film A and film B. And we have this model kind of on the opposite track where we've predicted K ratios. And so what we're trying to do is we're trying to just minimize this formula here. And gosh, I just realized my slide kind of didn't translate the way I wanted to, but we're basically summing the predicted K ratio by the measured K ratio. We're squaring that, summing it all up, and then taking the square root of it and trying to minimize that number. So you're changing thickness A and thickness B until you minimize this formula between the predicted and the measured K ratio there. And what you actually end up with is something that you consider a solution surface, so to speak. And that's what we're looking at here in this case. So this would be just a generic example, and I don't even remember what we used for element A, element B, but or sorry, the films of A and B. I think they were meant to be pure, but you have this case where based on your actual model that you collect, when you vary the thickness of A and B, you're actually going to meet some kind of absolute minimum, and that's really your solution that you bore from. So that's how we kind of came up with this example, the 60 and 33 nanometer, bullseye, so to speak. So the other questions that kind of come up that's really kind of it's different from regular EDS is what KV should I use, what line intensities do I measure, will the technique actually work? This is the kind of thing that's in this solver that I'll kind of demonstrate a little bit when we get over the system. Just to give you kind of some other quick examples, the other options that are out there that kind of work with Lair Probe or similar technique, I should say, we're really trying to look at something like ellipsometry. We're looking at XRF, or we're looking at FIB, and kind of saying, this Lair Probe option, it's something that it's relatively cheap compared to the other three options in a sense. We don't need to buy a $1 million FIB or anything like that. We got to have the EDS and the SEM to begin with, yeah, but we're not going up to the super high end there. The other thing that's nice compared to at least the FIB size is it's non-destructive. So we're able to, save the sample for further use. So just a comparison of the techniques there. Now, I'm going to brush through the applications a little bit quickly. I want to make sure we kind of get to the actual hands-on part of it here. But one of the obvious applications for us was kind of the lamella prep. If you're ever doing STEM work or have a FIB and you got to make lamella for STEM or TEM work. In this example, this was, we're looking at some nitride layers that we've seen, top down. Actually, I think this was a cross section that we looked at, but we were trying to figure out, how good are we resolving the nitride layers? What's the overall thickness of the lamella? And you can kind of see the thickness of the lamella is really on the higher side to really do a good job of STEM work in this case. But, the interesting part of this technique is when we first developed it, it involved you leaving the lamella actually attached to the OmniProbe tip and, removing your sample, kind of putting it into a milling position, mill it down, then actually rotate it to a measurement position. And it can be kind of free floating in space, if you will. I mean, it doesn't have to be on the stage per se. It just has to be under the beam so that we can take advantage of the EDS. But kind of an example here, this is just looking at different portions of the lamella, potentially looking at the gallium implantation that's been done by the ion beam in this case. But you can kind of see there's some regions up here where you see 135 nanometers of copper in a case, or this just the regular silicon, 115 nanometers of silicon in that example. But down at the bottom, where you've really milled down the bulk of the sample there, you're seeing as little as 18 to 40 nanometers worth of thickness there. Here's another example on a sample that's probably been polished a little bit better, but you can kind of see the different regions there in the chip. And this is still done completely on the OmniProbe tool. The other example that I have, and this is going into maybe the low thickness end of it, if you will, if you want to go that direction. This is an exfoliated disulfide flake, and this is something that even in the optical micrograph you can see that there's two distinct layers there, and we kind of expect them to be kind of this graphene-like structure where there's two separate layers, and the theory was roughly 6.5 angstroms between them, so less than a nanometer of difference. And when we actually measured it with Lair Probe, you can see the difference in the spectra there. You can kind of see that in this region that was suspected to be thicker, you had a taller moly and sulfur peak there, and then that you did on the on kind of the other layer there. And when you measured it out with the formula, you had almost exactly what you would expect. I mean, this is a little on the higher side. But it's about double the thickness, and you can kind of sit there and go, we're really talking about one monolayer versus two monolayers in this case. And this was something that we verified with AFM. So I thought this was kind of cool to bring in. This was something that was done with the Asylum AFMs, which is part of the Oxford group right now. But we measured off to the one layer. You could see about a 0.8 nanometer change, and jumped up to the second layer about another 0.8 nanometer change in height, measuring it with AFM. They took this a step further, and they went to actually tungsten selenide and moly disulfide heterojunctions with these films. And this was something that was kind of, can we do this with the different chemistries in a sense? And here was an example, and this is really kind of interesting at the end of the day, what you see here. And we tried to kind of color code the best we can in this case, but what you have is the tungsten selenide layer that you see in green here. And then there's a moly disulfide layer on top of it, but it appears that there's a single layer and then a double layer. And it's the type of thing where, again, when you look at it from the bulk spectrum there, it's really kind of hard to see the difference. If we zoom in on that moly and sulfur peak, you see there's actual distinction between the single layer and the double layer thickness there. So you can actually kind of say, hey, I know that tungsten and selenide are in there too, but I can see the difference in the moly disulfide as well. And again, this is something that we went through and just verified it, both with Lair Probe, and then we verified it with the AFM with the Kelvin Probe AFM there. So it's really possible to do stuff like this. The complication might be in nailing down your model and getting kind of densities of films exactly correct, but there's a lot of potential there. And just as a couple of the last slides here before we move over to the system, what's the accuracy look like? And this was something where two films were put down via ALD. You had hafnium oxide and aluminum oxide, and the actual thickness when you look at it, and I don't think I have the actual final number here, but what was interesting was, you see the Lair Probe measuring out about 28. The ellipsometry says it's about 33. The aluminum oxide 57 versus 52. So a little bit of error associated with it, but we're really doing some numbers that are pretty much equivalent with the ellipsometry. Another case was they looked at the stoichiometric ratio, and really kind of on par with what was measured via RVS in this case. So A lot of potential there, assuming you can kind of get the model right. Here's maybe a little bit more graphical example of this. This is a gold on nickel on silicon. And this is something that's been milled. I don't know if it's been milled or if it's just been actually just cleaved and then looked at the cross section. It looks more like a cleave to me than anything milled. But when you look at it, you're talking about a thickness of 55 nanometers on the gold, maybe in the ballpark of 120, 125 on the nickel. And if you look at it, maybe it's a little bit difficult to define where that gold nickel interface is, but when you look at the overall thickness, 187 nanometers agrees really well with what our numbers say, and really have about the right thickness of the gold and the nickel in that case. So on that, I'm going to switch over to the actual SEM microscope here. I think I just stopped my sharing on that side. And let me jump over to the, what I'll be showing you is the Aztec interface there. Okay. All right. It's going to take me a second or two to just get set up on the microscope side here. So the first thing I need to do is, are we sharing, by the way? Are we sharing?
Yes, it is sharing
okay.
the.
Okay.
Looks good.
I apologize. I'm just going to switch over to, Lair Probe's just another technique in the drop-down list here. And the other thing I didn't mention in the process was, Lair Probe's designed to take the spectrum from anywhere in the software. So if you had collected a map, say, and then went, oh, you know what, this is more like this, maybe I should be looking at this in Lair Probe. Build the model, and you might be able to bring the spectrum right over to Lair Probe. The caveat will be the optimization element, and we'll jump on that in a second here. So Lair Probe, I need to get the model set up first here, and that's not my model. Let me just clear this. So I start on silicon in this case, and the bulk material, it's just really easy to enter this, just silicon. I know it's 100%. I know it's my bulk material, so I'm not talking about thicknesses. So I'm just going to add above in a sense. And what I have is, pure films. They're just metal deposition layers here. So, the one that was closest to the sample is chromium. And if I keep going up, I had a copper layer, and then I had a gold cap layer on top of this. Now you can kind of see I'm typing these all in. I'm just saying it's gold, it's fixed. I know it's 100%. It makes life pretty easy for me, but what happens if you have something complicated, or what happens if you're looking at something over and over again? I do want to make sure people realize that there is a edit materials. There's kind of a materials database here. So if you're coming back to this a lot, unfortunately there's nothing in the list, but if you had a common material that you were always looking at, it's easy to just bring that in the list. And the other thing too is, if you have compound materials, if you're doing a silicon oxide, say, and you go, gosh, I really don't know if it's stoichiometric. That's a good guess, but you can actually change the concentration so that, it might be unknown, or it might be a difference with another element. So there's a lot of options for you to put in. And maybe one of the more critical ones is the density, because these metal depositions, I'm putting in the pure bulk density, and it's not probably the most accurate number, and it's probably the biggest source of error for me today. But what I need to do is now address the thicknesses of each of these. Now, I like to tell this story the way I was originally introduced to this sample, because someone handed me a bottle and said, take a look at this, this is kind of an interesting sample, and it said 30, 30, 30 on it. And the implication was they were each 30 nanometer thick layers. So let's build a model on that case. If I go back to all these, now they're not fixed thickness by any means. They're unknown. I'm just using 30 as a guess. So my nominal starting point is 30. Keep moving down the list. And I really have my model there. I mean, you can come back through and check them all really quick, but when you're happy, you know, you hit save. Other thing to keep in mind too, this isn't something that we expect you to do over and over again. So when you've saved these stacks, make sure you import them and export them so you have it. If you have to go to another microscope and measure it on a different microscope, I know we got Lair Probe on a couple of systems here at Nuance. Take them with you. They're you know, why reinvent the wheel kind of thing, right? So we have our edit materials over here. We have a simulate spectra here that I'll probably refer back to in a second here. But then there's the setup solver. And just as a bit of a funny laugh for everyone, the very first time I was introduced to the solver, not happy with me here. This is why you save your profile there. I think we might have lost it. Let me move quickly here rather than waiting for it. I just want to grab a sample here really quick on the copper. My model should still be there. Yep, okay, so my model's still there. A little bit high on the beam current. All right. So now I got a setting that I want. Now I'm going to come back to that setup solver really quick. I want to actually, now that I kind of got the beam settings about where I want them, what I'm going to do is I'm going to actually do my optimization element here. And I'm going to go down to optimize. And this is the probe current measurement. And the only thing to think about when you're doing Lair Probe is, you know, try to consider the materials involved, what accelerating voltage you think you might be at. Doesn't need to be perfect, but you want to give yourself an option to get to an optimization element. And I'm thinking, you know, anything under about 10 kV, silicon's a great one because we need a K series line. I can go to copper. Copper's going to work really well for me today. I'm at 20 kV, so I got a K line for me. That's probably going to be my choice today, and that's why I have the copper on the actual sample here. So I'm just going to check my settings, make sure they're about what I expected. Yeah, that's fine. And all I do is just measure it. And keep in mind that if you feel like the beam current is drifting a little bit, or you don't think it's really, really stable, make sure you just come back and run this beam optimization, this beam measurement. Make sure you run it every 15 minutes or every 30 minutes. You know, you don't want it tapering off by more than about 3 or 4% if you can help it. And the first time you do the measurement, it'll tell you the measurement's okay. It's as if it kind of says, all right, copper's the material now, and I've measured it here. And it uses the count rate on the calibration peak to kind of determine what the beam current is. And it's going to use that across the board going forward. So I'm just going to hit yes, and you can see it saves in my data tree over here. And I could work back, and I could come back to the sample here in a second. But I can use that information again, and I'm going to try this setup solver one more time really quick just to see if it'll be happy with it. Well, I think I've been caught off guard here. All right, I'm going to move past that. And I apologize that I can't share that with everybody, but basically our setup solver part of the software is really a means of kind of helping you through the idea of what might be a good what might be a good setup in terms of, you know all these different materials, you know what's unknown, things like that. What's the appropriate accelerating voltage that you use? And in this case, it might have told me a lower accelerating voltage. It's just making a recommendation to me based on a couple of things here. So again, I'm just going to retake the optimization one time, and then we'll actually go to the sample here. Okay, you can see how good the beam stability is on this one. We've measured it. It's been a couple minutes, but it hasn't dropped off by a fraction of a percent at that. So we're good to go. We know we have a stable beam, so we know we could probably work a while without ever having to drive back to the optimization element. But let me drive onto my sample now. Let me see if I can find it's kind of interesting to find potentially ugly spot on the sample here, because it might help show some differences in the film thickness even. Because I know I have a few pores in and around this sample here. So let me do this here. This looks kind of interesting here. That just actually looks like a film. Bear with me, I know you can't follow along here necessarily. We can try this one just for the sake of having a little bit more features in the field of view here. But I'm going to come over to the Lair Probe, and truthfully, I could run this as if I was in point and ID here as well. So a little bit ambitious on the resolution there that somebody had to start. Collect my image. And this is the case where I've forgotten. I do like to actually keep my beam measurements separate from my actual data. Not a requirement by any means, it's just me. So there's what we're looking at on the microscope. I'm wondering if that's a little pore there, if this is something that's a pore there. But when we're ready to acquire the spectrum, my settings should match exactly what I was doing on the optimization part. And I don't need to take a million counts, that's a bit excessive. But let's take a few points here. And I'm just going to do maybe a point right there. That looks like a pristine film there. Maybe take another one a little further out, and then maybe take one right on that guy there. And what I like to do, and this is the case, so remember, I said 30, 30, 30, and I was expecting, there we go. You can kind of see, I was expecting to see all these materials. I expected to see the chrome. I was not really expecting to see the aluminum, but the silicon and the base substrate, the aluminum, the chromium, the copper. Those were the elements that I expected to see. So one of the things I try to use is the simulate spectrum. And if we go over and look at that really quick, what's really interesting about this right off the bat is this is the simulated spectrum for the model. That's what you're seeing in the pink. And when you look at it really carefully, it's kind of about right for the gold. It's not right for the chromium, and it's nowhere near correct for the copper. So there's something already kind of telling about, well, my model versus my actual sample here is kind of interesting. And what I want to do before I go way down this rabbit hole is let me just go back and see what the results actually tell me. So I can go back to my confirm element here, and all I want to do is make sure I assign the proper X-ray lines for analysis here. Now I don't need the same ones over and over again. I don't need 2 copper lines. I don't need 2 gold lines. And since I have a high enough accelerating voltage, I'm just going to use the higher energy of the 2. And when I quantify this, what's really interesting is the gold is more or less about where I expected, about 30. The copper is way, 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 way thicker. And the chromium is, kind of maybe in the ballpark of what I expected. So, they're all off by a little bit percentage-wise. And again, I point the finger a little bit at the density. But I'm looking at this going, gosh, the copper's, astronomically higher than what I expected. I expected to be at 30. Well, what do the rest of them look like? If I look at spectrum 2, pretty consistent result there. If I look at spectrum 3, is it an actual pore? No, it actually looks like a little buildup of copper. So maybe there's a little copper nodule under it that was a little thicker. Maybe there's a defect in the chromium, but this is clearly not a flaw in the top of the film there. It looks like it's something more in the substructure that's kind of created that. I got some information there that's really kind of interesting. Here's where the kind of the trick for everybody is I went back to the person that grew this and just went, there's no way you have 30 nanometers of copper. And they looked at me incredulously and said, no, who said 30 nanometers of copper? I said, well, that's what the label says, 30, 30, 30. And he goes, look at it again, it says 30, 330. And a 0 had actually been wiped off the label, and it just shows how poor the lab quality can be. But I can assure you that when we went back to the people that actually worked on this, they said, no, it's actually supposed to be 300 nanometers of copper. So it was a big relief to me, but it at least proved just how far off you can be on your initial guess and get to a consensus answer here. Now, if I want to put this into a nice table and present it, that's where I can come to this level. And you can see it tells me what the different layers are. It tells me what the atomic composition is. And you kind of go, well, heck, I told you what that was. So just show me the unknowns. And you have a nice table here of thickness of the different ones. Now, I would be remiss if I didn't tell you that you can get way more complex than this. What you can do is I could go to a completely different region on the sample. And keep in mind, I kind of mentioned, someone asked a great question earlier about magnification. If I go to too low of a magnification, I go to the corner of this film, well, then I'm not helping myself, because I'll lose geometry of the detector and it might not be right. But here's an example of something I do. This is now at 6000x. And I'm going to come over here and use the line scan. And I'm just going to grab a new site. And again, I'm kind of curious about this defect just to see if it really is an issue or not. But I might not have enough data points at the same time. But I might actually acquire a line. I'm going to come in here and just make sure my settings are about what I expected. That looks great. And I'll draw a line across. I'll go right through that defect there. Hit start. And I can look at this map. I can look at this line scan all day and kind of look at it and go, is anything really changing? It looks like, yeah, it kind of looks like something's going up. The copper layer is a lot lower there. Yeah, it looks like it may be a defect in the structure just based on what we're seeing on the copper signal. But again, quantify that for me. That's where we're really going with this. So, with a line scan, I'll let this acquire for, we still have a couple minutes here. Let's let it acquire for maybe another 30 seconds, and I'll pull a spectrum off that. But better yet, what we can do is we can pull the spectrum off every single point along this line. And rather than, pulling 500 points out and plugging it through the algorithm, let's just break it up into line segments. I can break this up into about 15 or 16 line segments, and we can go from there. So let's try the defect first. So that'll be my spectrum here. I'll just pull that out. So spectrum 4, and don't forget to make notes for yourself. I always start to run with the generic labels, and then I forget what I was even doing with some of these things. So call it the defect. But once I'm done, let's see how this goes. Now, I don't really have enough counts maybe for any one individual point, but there's a tool in here to reconstruct the spectrum from every point on the line scan. And again, like I said, I don't think one point for every, having the spectrum for every point is worthwhile, but let's break it up into like 16 segments. So I'm just going to extract that. You can see the line segments that we've broken it up into. Kind of have a nice list there in the tree here, but let's go back to our layer probe and now punch these spectrum through the actual algorithm here. There's nothing wrong with me going, I'm going to use the defect, and I'm going to use the same, same operating parameters we had over here. And so when we count it here, you can see that there's just more material missing, and it's missing from the top half. We're not missing anything right on that chrome adhesion layer. We're missing some fraction of the copper, and we're definitely missing some fraction of the top gold surface there. So somebody's been trying to steal the gold right off this. Now, here's where it might be really valuable to you. You know, you want to see film thickness and uniformity across the sample. Let's use the full results table, customizable, and let's put in all these spectrum going across on the line scan. Let's highlight them all here. If you forget where you were looking, use the electron image. There's all your points. It's easier to just break them up. Now you can see where you were looking at. And again, have a nice table and it's showing me all these compositional numbers, but I just want to see the unknowns. I want to see how they change across the sample. And you can see in this example, they're pretty much nice and even across, but you kind of have some data points here. You can kind of see where min-max averages and standard deviations kind of well out. And that's on a simple line scan that took us all about 2 minutes. So, you know, again, I just want you to see the power in this algorithm. It's really just kind of an extra step in there to develop a model. And again, making sure you do the beam measurement. And after that, it's like doing regular work. And don't be afraid to pull from different sources. You know, pull from a map, pull from a line scan if it can help you solve problems here. So with that, I think we can move on to questions. And I haven't been able to look at the chat just yet.
Thank you so much, Mike. We do have some really great questions. One of the first questions is asking if you can measure oxidation layer thickness of metals or alloys.
Sure. That would be a perfect example of it, where you just, you know, you'd put the base layer down as your bulk, and then you'd specify the oxidation on the top. And you don't necessarily have to know the oxidation state. If you suspect it might be some kind of combination, you could leave it up as an unknown and put that into the formula as a potential.
Another question is, does Lair Probe work with samples that are not flat?
It's not going to be as reliable if they're not flat. That being said, if you feel like you can find a localized region that's relatively flat, I wouldn't hesitate to try it.
All right, one more quick question. Does Lair Probe work with DLC coated substrates?
DLC, diamond-like carbon, I'm assuming we're talking here. Interesting question. I would think it'd be a possibility, but the trick with something like carbon is always going to be the question mark of whether or not it's incorporated in the film or whether or not it could be contamination, and that's the real tricky part. So if you can keep your samples really, really clean, you got a really clean SEM that would work with this, then that's the method to shoot for with something like that.
And then we will just do this last one really quick to stay on time. So what is the minimum layer thickness that you can detect using this method?
So, you know, it kind of remains to be seen, but you know, if you saw the presentation, the example that was in there was a single monolayer of a moly disulfide, which was, you know, sub-nanometer differences there. So, you know, there really is the capability to go right down to the nanometer scale.
Thank you so much, Mike, and thank you everybody here attending the morning. Thank you both to Muto-san and to Mike for wonderful presentations and demonstrations. To everyone and everybody that helped organize the conference or this workshop, we really appreciate all of your help. So thank you.
Thanks, everyone. Thanks, everyone at Nuance. We really appreciate you putting this on and doing all the hard work.